In this video, we're going to be talking about combining functions. For functions f and g, the sum, difference, product, and quotient functions, f plus g, f minus g, f times g, and f divided by g respectively, are defined as follows. So it's pretty intuitive. If we have two functions f and g, we can create an entirely new function by either adding, subtracting, multiplying, or dividing those two functions. So let's see how it works in example 1. Let f of x be equal to 3 times the square root of x minus 2, and g of x equal x squared plus 5. Find and simplify the following. In part A, we want to evaluate f plus g of 4, and if you use this top definition here, we can rewrite this as f of 4 plus g of 4. So we want to evaluate f of 4 and g of 4, so I'm going to do that off to the side here. I have my f function, and anywhere I see an x, I'm going to replace it with 4. The square root of 4 is 2, so I have 3 times 2 minus 2, which is equal to 6 minus 2, which is equal to 4. And then we want to evaluate g of 4. So I'm going to square 4 and then add 5 to it. 4 squared is 16, and then adding 5 gives us 21. So f plus g of 4 is equal to 4 plus 21, which is equal to 25. So here, our final answer is 25. For part B, we want to evaluate and simplify f minus g of x, which, if we look at the formula here, we can rewrite this as f of x minus g of x. So I'm going to go ahead and fill in f of x, which is 3 times the square root of x minus 2. And we're subtracting off g of x. Now here we want to be very cautious to make sure we put either brackets or parentheses, because we're subtracting off the entire quantity of that function. And that's important because we're going to need to distribute this negative sign. If we do that, we get 3 times the square root of x minus 2 minus x squared minus 5. And then here we have these like terms that we want to combine, and that is going to give us negative x squared plus 3 times the square root of x, and then minus 7. So there's our answer for part B. In part C, we want to evaluate f times g of 0, which, if we look at the definition above, we can rewrite this as f of 0 times g of 0. And let's evaluate those off to the side here. So f of 0 is equal to 3 times the square root of 0 minus 2. The square root of 0 is 0, times 3 is still going to be 0, and so we get that this is equal to negative 2. And then g of 0 is equal to 0 squared plus 5, which is equal to 5. So this is going to equal negative 2 times 5, which gives us negative 10. In part D, we want to evaluate f over g of 9, and if we look back up here at our table, then we can rewrite this as f of 9 divided by g of 9. F of 9 is equal to 3 times the square root of 9 minus 2. The square root of 9 is 3. 3 times 3 is 9. 9 minus 2 is 7. And then g of 9 is equal to 9 quantity squared plus 5. So that's going to end up being 86. 7 over 86. Can't do much to simplify that. So here we have this is equal to 7 over 86. Let's talk about the domain of a combined function. The domain of f plus g, f minus g, and f times g is the intersection of the domains of f and g. The domain of f divided by g is the intersection of the domains of f and g with any points where g of x is equal to 0 removed. let's put this into action and practice with some examples. Example 2 says, let f of x equal the square root of x, g of x equal 3x plus 1, and h of x equal x minus 1. Find the domains of the following functions. So in part A, we are looking at the function f plus g of x, which is equal to f of x plus g of x. I can go ahead and just replace those. So f of x I can substitute in with the square root of x, and g of x I can go ahead and substitute in with 3x plus 1. So I get the square root of x plus 3x plus 1. So one way that we could go about this is thinking about the domains of each of these separately. So the domain of f of x, which is the square root of x, is all non-negative numbers. And then for g of x, this domain is all real numbers, since 3x plus 1 is a linear function, and unless we have a restricted domain, linear functions are always going to have a domain of all real numbers. Now, if I want the domain of f plus g of x, I would look at the intersection between these two sets. So I have 0, infinity, intersect, negative infinity to positive infinity. And if we take the overlap, or the intersection of these two sets, that's going to be 0, infinity. So there is our answer for part A. And so that's one way that we could think about it in terms of thinking about the two domains individually and then taking their intersection, but also look at our combined function. We have the square root of x plus 3x plus 1. You could also just look at that combined function and say, well, I can't really plug in a negative number into the square root of x. 3x plus 1, that's okay, I can plug in anything into that, but the square root of x I can't plug in a negative number, and so that's going to mean that my new combined function has a domain of 0 to infinity, including 0. Let's move on to part B. We have g over f of x, and rewriting that, that's the same thing as g of x over f of x, and g of x is 3x plus 1, and f of x is the square root of x. So I have my written out combined and simplified function, and looking at it, if we see that the denominator has the square root of x, then our domain is going to be very similar to the domain in the previous part of this question. However, now we can no longer include 0 since I have square root of x in the denominator. So for part B, my domain is going to be parentheses 0, infinity parentheses. So there's our domain for part B. For part C, we have h over g of x, which is equal to h of x over g of x. And h of x we see is x minus 1, and g of x is equal to 3x plus 1. And again, I can think about the intersections of the domains of the two original functions, or I can just take a look at my new function. I see that it's a rational function, and so because it's a rational function, I'm just going to go ahead and take my denominator and set it equal to 0, and then solve. I'm going to subtract 1 on both sides, and then divide both sides by 3, and we get x is equal to negative 1/3. So the x value that makes the denominator 0 is negative 1/3, meaning our domain is going to be all numbers, all real numbers that are not or exclusive of negative 1/3. So we have negative infinity to negative 1/3 parenthesis, union parenthesis, negative 1/3 to infinity, and this is our domain for part C. Now we're going to talk about a different way to combine functions, and that is called composition of functions. Before we get into that, let's do some more practice with evaluating other types of functions. So example 3 says, let f of x equal x squared minus 2. Find and simplify the following. Part A should look familiar. We have f of x plus h, which is the first part of the difference quotient formula. Anywhere I see an x I'm going to replace it with x plus h inside my original function. And I want to go about simplifying this. So be careful. As a friendly reminder, x plus h squared does not equal x squared plus h squared. This is a huge no-no, and we don't want to write that incorrectly like that. So how do we simplify x plus h squared? Well, there's a couple ways. X plus h squared is the same thing as x plus h times x plus h, and from here you can either FOIL or use the box method. I am a huge proponent and fan of the box method because foiling, that acronym, really only works if you're multiplying two binomials together, and with the box method it's a lot more organized. So also notice that here I have my like terms in my diagonal, so if I combine this, that's going to be x squared plus 2xh plus h squared. So here I have x squared plus 2xh plus h squared minus 2, and there are no like terms that we can combine, so that is our final answer for part A. For part B, we're trying to evaluate f of 2x, so in my original function, anywhere I see an x, I want to replace it with 2x, and we want to simplify this. So if I multiply 2x times 2x, that gives me 4x squared, and then we have our minus 2. There's no like terms that we can combine, so our final answer is 4x squared minus 2. In part C, we want to evaluate f of y minus 1. So we have y minus 1 quantity squared minus 2. I'm going to go ahead and use the box method again. So I have y minus 1, this is y squared, negative y, and positive 1. So combining like terms, we get y squared minus 2y plus 1 minus 2, and plus 1 minus 2 ends up giving us minus 1. And so here is our final answer for part C. Recall that functions take an input and map it to a specific output. Let's take a look at a function g, where the input value is a person and the output is the city that person was born in. Let's take a look at another function f, where the input is a city in the world and the output is the median household income of that city. Let's evaluate these functions at some specific examples. So we have a table here, and for g, we have g of Barack Obama is equal to Honolulu, g of Kamala Harris is equal to Oakland, and so on and so forth. So we have a few people. If we throw them into the g function, the output that comes out is the city that the person was born in. For f, our f function, our input is a city, and then the output is the median household income for that city. And so we have a few examples in this table for f as well. And the source for this is the US Census Bureau in the year 2021 as far as the median household incomes. So here we have a list of questions. What do you think the domain and range of g are? So for g, the domain is going to be all people in the world. And then the range, or the output, is going to be all cities in the world. For f, the next question asks about the domain of f. So the domain of f would be all cities in the world. And then the range would be, notice that the output values are numbers. So this one we could probably write it in interval notation. And so I'm going to say the median household income of these cities can range anywhere from 0 to infinity. And then what is g of u? So you, the reader, or you, the viewer, if you enter in yourself into the g function, what is your output? And then is there anything that you find odd about the table above? Something that I find odd is that none of these cities match any of these cities in the two columns. So I find that kind of strange. In the previous table, you might have been curious about the median household incomes of some of the cities that the people in the first column were born in. It turns out that we can actually make a completely new function from the functions f and g. Let's take a look at a visual representation of what this new function might look like. Imagine two fictitious people, Cora and Aang. Let's look at their mappings down below. So we talked about the domain of the g function, which was people in the world, and then the range of g was cities. And then the domain of f was cities, and then the range of f was median household incomes that ranged between 0 and infinity. So what is happening here? Well, I'm taking a person from the domain of g. This person, her name is Cora, and she maps to Bellevue because that is the city that she was born in, and then Bellevue maps to a median household income of $129,000 and $129,497. And then we have this other person, his name is Aang. He, when plugged into the g function, maps to Tacoma because that's the city that he was born in, and Tacoma has a median household income of $64,457. So what essentially we're doing is we're looking at two functions and we're taking the input of one of the functions, then getting an output, and then taking that output and plugging it into a completely different function and then getting a new output. So if you'll notice here, we have this notation at the bottom. It looks like the word fog, but it is actually the notation for composition. So the new function that we create maps a person to the median household income of the city that they were born in. This new function is called f composed with g, and that's read as follows. So that circle is not an O, it's not the letter O, it is an open circle, and this open circle is used to denote composition or a composite function, which is again when you take one function and plug it inside of another function. A question: assuming that a person stays in the city that they were born in throughout their childhood, do you think that the median household income of that city will have effects on their life? If so, in what ways? Leave your answers in the comments if you have some ideas or thoughts about this question. So if f and g are two functions, the composition of f with g is the function. This is read as f composed with g of x, which is equal to f of g of x. So we're taking g of x and plugging it into the f of x function in this case, provided g of x is in the domain of f of x, and the domain of f composed with g is always a subset of the domain of g. So here is just a quick visualization again. We have these sets. These sets we're calling x, y, and z, and they represent domains and ranges for the two functions. And we're taking an element of the domain and mapping it using the g function, and then its output is g of x, and then that's getting mapped to f of g of x in this second function. Example 4 says, let f of x equal the square root of x, g of x equal 2x minus 1, and h of x equal x squared. Find and simplify each composite function and give its domain. So in part A, we are trying to find f composed with g. So here is a more detailed notation. We have f composed with g of x, which is the same thing as f of g of x. So what we're doing now is I want to replace g of x in this with 2x minus 1. So if we do that, that's going to be f of 2x minus 1. And we know that the f function is equal to the square root of x. So now I'm going to take 2x minus 1 and plug it into that anywhere I see an x. So then this is going to become the square root of 2x minus 1. So that is our composite function for part A. And we also want to come up with the domain of that function. So because we are dealing with a square root, I need it so that 2x minus 1 is greater than or equal to 0. If I add 1 to both sides of this inequality and then divide by 2, I get x is greater than or equal to 1/2. And so our domain for this new composite function is bracket 1/2 comma infinity, and there is our domain. In part B, we are dealing with G composed with F, and composition is not commutative. What that means is G composed with F is not the same thing as F composed with G. There are a couple of special instances where this is true, but in most cases it's not true. And something that we can note is something like addition is commutative because F plus G is the same thing as G plus F. So this is something we say that it has the property that it is commutative, but composition is not commutative. Okay, so we want to do G composed with F of x, which is equal to G of F of x. So f is on the inside. I'm going to replace f with the square root of x, and then now I'm going to take the square root of x and plug that into my g function. So that's going to give me 2 times the square root of x minus 1. Notice that this is not the same function that we got in part A. If I want the domain of this thing, I cannot take the square root of a negative number, so my domain is going to be 0 to infinity. So there are our answers for part A and B. Let's go ahead and move on to parts C and D. Alright, so it looks like we have the word hog, but that's not what that is. It's read as h composed with g, and that is equal to h of g of x. So here now I'm going to replace g of x with 2x minus 1, and then anywhere I see an x in my h function, I'm going to replace it with 2x minus 1. So I'm going to have 2x minus 1 quantity squared. I'm not going to require that you multiply this out, so it's fine that you leave it like this. This is a quadratic function, and the domain of a quadratic function, unless restricted, is always going to be all real numbers. So here's the domain for part C. And in part D, we have f composed with h of x, meaning h is our inner function. And so h of x is equal to x squared. So we have f of x squared. And if I throw that into my f function, that's going to give me the square root of x squared. And hopefully you remember from intermediate algebra, the square root of x squared is equal to the absolute value of x. So here is our function, and then our domain is going to be all real numbers because we can plug in anything into the square root function. So our domain for this is going to be all real numbers. And that is the end of example 4. Example 5 says, given that f of x is equal to negative 2x plus 1, g of x is equal to x squared, and h of x is equal to negative 1/2 x plus 1/2, evaluate the following expressions. In part A, we want to evaluate f of negative 6. So anywhere I see an x inside my f function, I'm going to replace it with a negative 6. And we want to simplify this. Negative 2 times negative 6 is positive 12, plus 1 is equal to 13. In part B, we want to evaluate g of -3. So that's going to give us -3 quantity squared, which is 9. H of 4, I'm going to go ahead and plug in 4 or replace x with 4. And I don't want to forget about the plus 1/2. -1/2 times 4 is -2. And then we have plus 1/2. And if we find a common denominator, that's going to end up being -3/2. In part D, we want to find f plus g of x, which is the same thing as f of x plus g of x. So we have -2x plus 1 plus x squared. So I'm just going to rewrite the order of that. So we have x squared minus 2x plus 1. And I'm going to skip parts E and F. Maybe we can move on to part H. So we want to evaluate h of g of 8. So if we evaluate g of 8 first, we get h of 8 squared, which is equal to h of 64. So now I want to take 64 and plug it into my h function. So half of 64 is 32, and it's going to be negative plus 1/2. And if we simplify that, that is going to be -31.5. Let's move on to k, because k is the first one where we're composing 3 different functions. The way we deal with something like this is read as f composed with g composed with h of 3, and now we want to simplify the inside part. So h of 3 would be -3/2 plus 1/2, so that's going to end up being -1. So then we would have f of g of 1. If I plugged in 1 into the g function, that is going to be f of 1 squared, which is just f of 1. And then if I take 1 and plug that into my f function, that's going to be -2 times 1 plus 1, which is -2 plus 1, which is finally equal to -1. So k, the answer is -1. And you can have some more practice. I've put the answers on the screen in this peach-colored box to the rest of these parts.